Continuing now with section 4.2, we want to explore further the inverse relationship between exponential and logarithmic functions. And this actually goes back to something you studied in chapter 2. There is actually an algebraic method of finding the inverse of a function for a given one-to-one function. And that method is to interchange the rules of x and y. So suppose we attempt to find the inverse of the exponential function f of x equals a to the x. If we write this function as y equals a to the x, just replacing f of x with y, which we can certainly do whenever it's convenient. If we interchange x and y, y equals a to the x would then become x equals a to the y, or switching the sides, a to the y equals x. But this last exponential equation, a to the y equals x, is equivalent to the logarithmic equation y equals log base a of x. So in taking an exponential function and interchanging the rules of x and y, we actually produce a logarithmic equation, that is a logarithmic function. So we have verified the following fact, that exponential and logarithmic functions are indeed inverses. If f of x equals a to the x, then f inverse of x is log base a of x. That is, the inverse function is a logarithmic function with the same base as the exponential function. Example 7 will have us look at the inverse relationship for a particular pair of functions, the exponential function y equals 2 to the x and the logarithmic function y equals log base 2 of x. We're going to graph these, and actually we have previously graphed these functions. Y equals 2 to the x was graphed in the section 4.1 notes, and y equals log base 2 of x we just graphed just in the previous video. So for y equals 2 to the x, what we might choose is x equal to negative 3, negative 2, negative 1, 0, 1, 2, and 3. And then the y's are 2 raised to these different powers. So the y's would be 2 to the negative 3 is 1/8, 2 to the negative 2 is 1/4, 2 to the negative 1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. And then I can plot those points in the xy plane. So we have negative 3, 1/8 is about there, negative 2, 1/4, negative 1, 1/2, negative 1, 1/2, then 0, 1, 1, 2, 2, 4, and 3, 8. So you can see I've drawn a curve through those points, and that's the graph of y equals 2 to the x, this exponential function. Now if we graph y equals log base 2 of x, we just graphed this, so I'm not going to spend too much time talking about this, but essentially since this function, this logarithmic function, has the same base as the corresponding exponential function, it has to be the inverse of y equals 2 to the x. So basically all we need to do is interchange the rules of x and y. So the y's from the previous table will become the x's for the table for the logarithmic function. So we have 1/8, 1/4, 1/2, 1, 2, 4, and 8. And then the y's are the x's from the previous table. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. And then we'll plot those points. 1/8, negative 3 is about here. 1/2, negative 2 about here. Or excuse me, 1/4, negative 2. 1/2 -1, 1 0, 2 1, 4 2, 8 3. So now you can see I've drawn a smooth curve through this second set of points. That's the graph of the base 2 logarithmic function. Now to see the inverse relationship between these two graphs, I'm going to put one more graph in here, and it's going to be the diagonal line passing through the origin at a 45-degree angle. Okay, and this is the graph of y equals x. And when we put that diagonal line in, then we should see a symmetry when we look at the exponential and logarithmic graphs together with this line, that they are symmetric about the line y equals x. And this is a property that we talked about back in chapter 2 that we see when we compare the graphs of functions that are inverses. The graph of the logarithmic function is the reflection of the graph of the exponential function across this diagonal line y equals x. And this is a consequence of interchanging the roles of x and y. When we move a point, say the point 2 4 here, to the point 4 2 here, it causes a reflection of the point across that diagonal line, and every point gets reflected the same distance across that diagonal line, which causes this overall reflection effect to occur. Moving to the next page now, the properties log base a of a to the x equal to x and a to the log base a of x equal to x, which we saw in the list of properties of logarithms from a little bit earlier. I mentioned this at that time, that these are sometimes referred to as cancellation properties of logarithms. They can also be called inverse properties. So inverse or cancellation properties of logarithms, since they can be derived from the inverse relationship between exponential and logarithmic functions. Let me demonstrate this, the first property listed, by looking at example 8. Verify the first inverse property by letting f of x equal a to the x, f inverse of x is log base a of x, and performing the function composition f inverse of f of x. Now, you may recall from chapter 2 that anytime we do a composition of a function with its inverse, there's always a cancellation that occurs. So f inverse of f of x equals x, and f of f inverse of x equals x. What happens when we perform the function composition shown here for these particular functions? F inverse of f of x, if we work from the inside out, f of x is a to the x. So it's f inverse of a to the x. And what is f inverse? F inverse says whatever you plug into it, it goes into a logarithm, base a. So that would be log base a of a to the x. But we know by properties of functions and their inverses that anytime we perform this function composition, it always simplifies to x. So what we obtain when we look at this final result here is one of those two, the first one, that is, this one here, one of those two inverse properties of, or cancellation properties of logarithms. Log base a of a to the x equals x. So I just wanted to show you that this can also be understood in terms of the composition of a function with its inverse always producing a cancellation effect. there are a couple of particular logarithmic functions that are used quite a bit in applications and are worth mentioning separately. One of those is the base 10 logarithm, which is also called a common logarithm. For common logs, we may write log base 10 of x simply as log x. So if you see log x and you don't see the subscript, you don't see the base, you assume that the base is 10. The values of common or base 10 logarithms can be evaluated directly on a calculator using the log key on your calculator. So if you want to evaluate, say, log of 20.5, this would be understood to be the base 10 logarithm of 20.5. Then all you need is to press your log key. So you're going to press your log key, and then you're just going to enter 20.5. And what we would obtain, the log base 10 logarithm of 20.5 to 3 decimal places is approximately 1.312. So what this means is that if we were to raise 10 to the 1.312 power approximately, that should give us about 20.5. So that can just be done directly on a calculator. There's a second logarithm, perhaps even really more important, and that's the base e logarithm, where e is approximately 2.72. And we introduced this irrational number in the section 4.1 notes. This is called a natural logarithm, and it has its own special notation. The natural logarithm, the base e logarithm, is written ln of x, and ln of x is equal to log base e of x. So ln of x is a base e logarithm. Now, the properties of base e logarithms are similar to those of other logarithms, but because the notation is different, the properties may look a little bit different. So the basic properties of logarithms can now be restated for natural logs by letting the base a equal e. So log base a of 1 equal to 0 becomes ln of 1 equals 0. Log base a of a equals 1 becomes ln of e equals 1. Log base a of a to the x equal to x becomes ln of e to the x equals x. And a to the log base a of x equal to x becomes e to the ln of x equals x. So when we say, for example, ln of e equals 1, that's like writing log base e of e, excuse me a second. That's like writing log base e of e equals 1, for example. But rather than writing log base e, we just write ln. Values of natural logs can also be evaluated directly on a calculator. And for this purpose, you use a different key. You use the ln key, ln. And for this one, you would, for ln of 20.5, you would just press the ln key and then enter 20.5. And the calculator would show us that ln of 20.5 is approximately 3.020. And you can check that for yourself to make sure that you know how to perform that computation. Finally, we can also define the natural logarithmic function to be the function defined by y equals ln of x. Note that the exponential form of this equation is e to the y equals x. The properties of this function are like those of other logarithmic functions. In particular, if f of x equals e to the x, then the inverse function is ln of x. So e to the x and ln of x are inverses of each other. This concludes the section 4.2 notes.